For as long as humans have walked the earth, we've looked up at the night sky and felt that irresistible pull, the kind of awe that sends shivers down your spine. Those tiny points of light aren't just stars, they're keepers of ancient secrets, whispering stories that have shaped civilizations, guided explorers, and sparked wars. Think about it, every culture, from the Babylonians to the Aztecs, wove their own myths into the cosmos, turning constellations into gods, heroes, and even warnings. But here's the twist: what if those myths weren't just stories? What if they were clues hidden in plain sight, waiting to reveal the universe's deepest mysteries? Tonight, we're diving into 35 of these celestial legends, each one a puzzle piece in humanity's grand quest to understand the stars. Picture this: a desert astronomer thousands of years ago, tracing the same patterns we see today, but seeing them as messages from the divine. Or a medieval scholar risking everything to prove that comets weren't omens of doom, but cosmic wanderers following invisible laws. These myths did more than inspire, they laid the groundwork for astronomy, navigation, even our modern calendars. And yet, buried beneath their poetic veneer are truths so startling, they'll make you question everything you thought you knew about the night sky. So why does this matter now? Because these stories aren't relics of the past, they're proof that curiosity, our relentless need to look up and wonder, is what drives progress. Whether it's the myth of Orion's eternal chase or the Chinese legend of the Weaver Girl and the cowherd, each tale holds a kernel of scientific insight waiting to be cracked open. By the time we're done, you'll see the stars differently, not just as distant suns, but as silent witnesses to humanity's greatest triumphs, failures, and unanswered questions. Ready to unravel the secrets written in the sky? Let's begin. We've all heard the phrase, the dark side of the moon, conjuring images of a place forever shrouded in eternal night, a realm untouched by sunlight, mysterious and unchanging. But here's the truth: it's one of the most misunderstood concepts in astronomy. The so-called dark side isn't actually dark at all. Thanks to a phenomenon called tidal locking, the same side of the moon always faces Earth, but that doesn't mean the other side is forever in shadow. In fact, sunlight bathes every part of the moon over the course of its orbit. It's just that we never see the far side from our vantage point here on Earth. The Apollo missions gave us our first real glimpse of this hidden hemisphere, and what they found shattered centuries of speculation. Astronauts orbiting the moon saw the far side illuminated just as brightly as the near side, with craters, mountains, and plains basking in the sun's glow. So why did the myth persist for so long? Blame it on culture, not science. From ancient folklore to Pink Floyd's iconic album, the idea of a perpetually dark moon captured our imagination, weaving itself into stories and songs. Even the term dark side stuck because it sounded more poetic, more enigmatic than the technical reality. But the real irony, the far side of the moon isn't even the side that's truly dark. During a new moon, when the near side is facing away from the sun, that's the part plunged into shadow. Meanwhile, the far side is fully lit, invisible to us but blazing with sunlight. This cosmic dance of light and shadow has been playing out for billions of years, a silent reminder that the universe often defies our simplest assumptions. So next time you gaze up at the moon, remember, there's no permanent darkness, just perspectives we haven't seen yet. For centuries, sailors and travelers have placed their trust in the North Star, believing it to be the brightest beacon in the heavens, a celestial lighthouse guiding them through treacherous seas and endless deserts. But here's the surprise: Polaris, the star we call the North Star, isn't even in the top 20 brightest stars visible from Earth. In fact, it's only about the 50th brightest in our night sky. So how did this relatively modest star become such a legendary guide? The answer lies not in its brilliance, but in its position, a cosmic accident of geography that made it the unwavering anchor of the northern sky. While stars like Sirius, Vega, and Arcturus outshine Polaris by a staggering margin, none of them share its unique claim to fame. It sits almost perfectly aligned with Earth's rotational axis. Unlike other stars that appear to dance across the sky as the night progresses, Polaris holds nearly still, a fixed point around which the entire northern heavens revolve. Ancient navigators quickly realized its value no matter where you were in the northern hemisphere. The angle between Polaris and the horizon would reveal your latitude. Viking explorers used it to cross the North Atlantic. Underground railroad conductors whispered instructions to follow it to freedom. Even modern pilots still check its position as a backup to GPS. But why isn't Polaris brighter? Blame the fickle nature of stellar physics. A star's apparent brightness depends on both its real luminosity and its distance from Earth. Polaris is actually a supergiant shining with 2,000 times the Sun's energy, but it's also 400 light-years away, diluting its glow to a mere flicker by the time it reaches us. Meanwhile, Sirius, the true brightest star in our sky, is only 8 light-years distant, making its intense light impossible to miss. The irony: Polaris wasn't always our North Star, nor will it be forever. Earth's axis slowly wobbles over millennia, a motion called precession that gradually shifts which star holds the title. 14,000 years ago, dazzling Vega was the pole star, and in 12,000 more years, it will be again proof that even the steadiest celestial landmarks are part of a much grander cosmic dance. So the next time you spot Polaris, remember, its power isn't in its brightness but in its constancy. In a universe of swirling stars and fleeting comets, it's the one that stays put, a reminder that sometimes the most reliable guides aren't the flashiest but the ones you can always count on. That streak of light flashing across the night sky, what we call a shooting star, has inspired wishes, prophecies, and legends for thousands of years. But here's the twist: those fleeting sparks have nothing to do with stars at all. They're cosmic debris, often no larger than a grain of sand, vaporizing in a blaze of glory as they slam into Earth's atmosphere at speeds reaching 160,000 miles per hour. The friction from tearing through the air heats these tiny fragments white-hot, creating the brilliant trails we see from the ground. Ancient civilizations didn't know this, of course. To them, these sudden flares in the heavens were omens or celestial battles. The Greeks believed they were stars shaken loose by the gods, plummeting to Earth like embers from a divine fire. Norse mythology described them as sparks flung from the hooves of Odin's 8-legged horse, Sleipnir, as he raced across the sky. And in some Native American traditions, shooting stars carried the spirits of ancestors returning to visit the living. These interpretations reveal something profound. Even before science explained the phenomenon, humans saw patterns and meaning in the chaos of the cosmos. Today, we know these events as meteors, and when they come in swarms, we get meteor showers, one of nature's most reliable light shows. The Perseids in August, the Leonids in November, or the Geminids in December each originate from clouds of debris left behind by comets or asteroids. For instance, the Perseids are cosmic dust from comet Swift-Tuttle, which last passed near Earth in 1992 and won't return until 2126. Yet every summer, Earth plows through that ancient debris field, igniting dozens of meteors per hour. What's truly remarkable is how fragile these celestial fireworks are. A typical meteoroid burns up completely between 50 and 70 miles above the ground, never reaching the surface. The rare few that survive the inferno and land as meteorites are often just pebbles, yet they've fetched millions at auctions, prized as tangible pieces of the universe. So the next time you see a shooting star, remember, you're witnessing a fragment of cosmic history, perhaps older than our solar system itself, making its final, fiery bow. And those wishes we whisper, they're part of a tradition stretching back to the earliest stargazers, proof that some magic survives, even when the science is laid bare. One of the most stubborn myths about human achievement claims that the Great Wall of China is the only man-made structure visible from space. It's been repeated in textbooks, documentaries, and even by teachers as a testament to its colossal scale. But here's the reality. Astronauts orbiting Earth have confirmed time and again the Great Wall isn't visible to the naked eye from space, at least not in the way we imagine. Why does this myth persist? Part of it stems from a simple misunderstanding of scale. From low Earth orbit, roughly 200 miles up, the width of the Great Wall is comparable to a single human hair viewed from a distance of 2 miles. Its stones blend seamlessly with the natural terrain, making it nearly indistinguishable from rivers, roads, and mountain ridges. Even the International Space Station's vantage point, which offers breathtaking views of city lights and sprawling metropolises, doesn't reveal the Great Wall without magnification. Astronaut Leroy Chiaro famously photographed it from the ISS, but only under perfect lighting conditions and with a high-resolution camera, far from the dramatic, seen from space narrative we've been sold. The myth's origins reveal more about human pride than orbital mechanics. Early 20th century speculation, fueled by awe at the wall's length, over 13,000 miles when all its branches are counted, led to exaggerated claims. People wanted to believe something so monumental could defy earthly limits, becoming a beacon of human ingenuity visible even from the cosmos. The irony. Smaller, brighter structures like airports and highways are far more discernible from space due to their reflective surfaces and geometric patterns. But there's a deeper lesson here. The myth thrives because it speaks to our desire to leave a mark on the universe, to build something so grand it transcends our planet. In truth, the Great Wall's invisibility from space doesn't diminish its wonder. It's still a staggering feat of engineering woven into the landscape like a thread of history. The real marvel isn't whether it can be seen from orbit, but how it endures as a symbol of perseverance, connecting us to the countless hands that built it, stone by stone, century after century. So the next time someone proudly declares the Great Wall's visibility from space, you'll know the truth. Its greatness was never about being seen from afar, but about the stories it carries, the silent, steadfast witness to human ambition etched into the earth itself. Ask any child to draw the sun, and they'll instinctively reach for a yellow crayon, a habit so universal it feels like cosmic law. But here's the reality: the sun isn't yellow at all. It burns with pure white light, a fact anyone can confirm by looking at sunlight through a prism, or even the stark white glare of snow reflecting its rays. So how did this blazing white star become so firmly painted as yellow in our collective imagination? The answer lies in the very air we breathe and the way our ancestors tried to make sense of the heavens. Earth's atmosphere acts like a celestial filter, bending and scattering sunlight as it travels to our eyes. Shorter blue wavelengths get scattered in all directions, a phenomenon called Rayleigh scattering, which is why the sky appears blue during the day. But during sunrise and sunset, sunlight takes a longer path through the atmosphere, filtering out more of the blue and green light, leaving behind the warmer hues of yellow, orange, and red. These golden moments, when the sun hangs low and fiery, left such a vivid impression on early cultures that they cemented the idea of a yellow sun in myths and art. The ancient Egyptians depicted Ra, their sun god, with golden skin. Chinese cosmology associated the sun with the color yellow, linking it to the element of earth and the center of all things. Even in Renaissance paintings, the sun was often gilded in yellow ochre, echoing the tones of dawn and dusk rather than midday's harsh white light. But the sun's true color holds clues to its nature. White light reveals that our star is a G-type main sequence star, fusing hydrogen into helium at temperatures around 9,900 degrees Fahrenheit. If you could stand in the void of space and gaze at it unprotected, its brilliance would overwhelm your eyes. No trace of yellow, just searing white. Astronauts in orbit confirm this, describing the sun as a blinding, colorless orb against the blackness of space. The myth persists because we're ground-bound creatures, forever seeing the sun through the lens of our atmosphere's ever-shifting palette. Yet there's poetic truth in the yellow sun idea. Cultures worldwide tied its warmth to life, harvest, and vitality associations that still resonate today. Science may strip away the golden hue, but it can't erase the sun's symbolic power. After all, whether white or yellow, it remains the force that spins the seasons, fuels photosynthesis, and lights the stage for every human story ever told. So next time you squint at the sky, remember, you're not just seeing a star, you're witnessing a cosmic chameleon, its colors shaped as much by Earth's air as by the fires raging at its core. Black holes have long been painted as cosmic vacuum cleaners, devouring everything in their path with an insatiable hunger, a terrifying image straight out of science fiction. But the reality is far more fascinating and nuanced. While black holes do wield immense gravitational pull, they don't indiscriminately suck matter in like some kind of interstellar Hoover. Instead, their influence operates under precise, mind-bending rules governed by Einstein's theory of relativity. Let's start with the event horizon, that infamous point of no return. Picture it as an invisible threshold surrounding the black hole, where gravity becomes so strong that not even light can escape. Cross this boundary, and there's no turning back, but here's the catch. You'd have to get dangerously close to feel its grip. From a distance, a black hole's gravitational pull behaves much like any other massive object. If our sun were magically replaced by a black hole of equal mass, Earth's orbit would remain unchanged. The planets would continue their graceful dance, oblivious to the swap, because gravity depends on mass, not the object's density. Now, if you did venture too close, you'd encounter one of the universe's most brutal phenomena, spaghettification. This isn't just a quirky term, it describes the grotesque stretching and compressing your body would endure as tidal forces overwhelm you. Imagine being pulled feet first toward the black hole. The gravity at your feet would be exponentially stronger than at your head, stretching you like taffy while simultaneously squeezing you sideways. The result: a human noodle torn apart atom by atom before crossing the event horizon. But black holes aren't just destructive monsters. Stephen Hawking revolutionized our understanding by proposing they emit radiation, now fittingly called Hawking radiation. Quantum mechanics suggests pairs of particles constantly flicker in and out of existence near the event horizon. Occasionally, one falls in while the other escapes, carrying energy away. Over eons, this slow leak causes black holes to evaporate, a process so gradual that a typical black hole would take longer than the current age of the universe to vanish. So why does the sucking myth persist? Blame pop culture. Movies depict black holes as whirlpools swallowing entire starships, but in truth, matter usually spirals in gradually, forming glowing accretion disks as friction heats it to millions of degrees. These disks emit blinding X-rays visible across galaxies, and sometimes power jets of particles shooting out at near light speed, proof that black holes aren't just takers, but creators of some of the universe's most spectacular light shows. The next time you hear someone describe black holes as cosmic vacuum cleaners, you'll know the truth. They're more like meticulous sculptors, shaping spacetime with precision and occasionally offering glimpses into the laws that govern all of existence. Their real power lies not in mindless destruction, but in revealing just how strange and beautiful the universe can be when pushed to its limits. For thousands of years, the Big Dipper has been one of the most recognizable shapes in the night sky, a celestial ladle guiding travelers, inspiring myths, and even serving as a makeshift clock. But here's something that might surprise you. The Big Dipper isn't actually a constellation. It's an asterism, a smaller, unofficial pattern within a larger constellation, in this case, Ursa Major, the Great Bear. This distinction might seem like cosmic nitpicking, but it reveals how human imagination has shaped the stars into stories, tools, and maps across cultures. The Big Dipper's 7 bright stars form only part of Ursa Major's sprawling outline, which ancient Greeks envisioned as a bear with an improbably long tail. Other cultures saw entirely different figures. The Chinese viewed it as the chariot of the heavenly emperor, while some Native American tribes interpreted it as a great bear pursued by hunters. The name Big Dipper itself is distinctly American, coined by settlers who saw a water scoop in its shape. But regardless of what people called it, this star group became a universal tool for wayfinding. The 2 stars at the end of the Dipper's bowl, Merak and Dub, point directly to Polaris, the North Star, making them critical for navigation long before compasses existed. What makes asterisms like the Big Dipper so enduring is their simplicity. Unlike the 88 official constellations recognized by astronomers today, which often require creative leaps to see their supposed shapes, asterisms are bright, compact, and instantly recognizable. They're the shortcuts of the night sky, the patterns everyday observers notice first. Orion's belt is another famous example, 3 aligned stars that stand out even in light-polluted cities, though they're just a tiny fraction of the Orion constellation. The Big Dipper's stars share another secret. They're not just random neighbors in the sky. 5 of them, Merak, Dubhe, Phector, Megrez, and Alioth, are moving together through space as part of a loose stellar group called the Ursa Major Moving Cluster. Born from the same cosmic nursery roughly 500 million years ago, these stars are racing through the galaxy in unison, while the other 2, Alkaid and Mizar, happen to be passers-by aligned by chance from our vantage point. This blend of myth and science is what makes the Big Dipper so compelling. It's a reminder that the night sky is both a canvas for storytelling and a laboratory for discovery. Whether you're using it to find north, spotting its faint companion star Alka as a test of eyesight, or simply admiring its familiar shape, you're participating in a tradition that spans millennia, one where imagination and observation meet among the stars. From the moment you're born, the stars supposedly whisper secrets about your destiny, your strengths, your flaws, even who you should marry. Astrology claims the alignment of planets at your birth imprints a personality blueprint, one that horoscopes refine daily. But here's the unromantic truth. There's no scientific evidence linking celestial bodies to human behavior. What does shape our belief in astrology? A cocktail of psychology, coincidence, and our brain's love of storytelling. Take the Barnum effect, named after the showman P.T. Barnum, who famously said, "There's a sucker born every minute." It's the tendency to accept vague, flattering descriptions as uniquely accurate. Psychologist Bertram Forer demonstrated this by giving students a personalized personality test, then revealing everyone received the same generic feedback. You have a great need for others to like and admire you, or at times you're extroverted while at others you're shy. Overwhelmingly, students rated these statements as uncannily specific to them. Sound familiar? It's the same trick horoscopes pull off daily. Confirmation bias turbocharges the illusion. We remember the times a horoscope got it right, like predicting a surprise encounter while ignoring the dozens of misses. A study in the journal Nature had participants read both real and fake horoscopes. Even when told some were fabricated, people rated the fake ones as equally accurate if they aligned with their experiences. Our brains are pattern-seeking machines wired to cling to hits and discard misses. Then there's the glaring scientific problem. Astrology assumes planets' gravitational or electromagnetic forces influence personality. But the gravitational pull of the delivering doctor in the room outweighs Mars by orders of magnitude. As for constellations, Earth's axial wobble over millennia, precession means the zodiac signs no longer align with their original stars. Your Leo birth month might actually correlate with Cancer in the sky. Yet astrology endures because it speaks to deeper human needs, the craving for guidance in chaos, the comfort of feeling seen. Its real magic isn't in the stars, but in how it mirrors our desire to believe there's order, and maybe even meaning, written in the heavens. Long before telescopes revealed the true nature of our galaxy, cultures across the world gazed at that hazy band of light arching across the night sky and spun stories to explain its ethereal glow. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, believing it was formed by droplets from the goddess Hera's spilled breast milk. In Japan, it was the celestial river Amenagawa, where the deities Oriheim and Hikoboshi, the weaver and the herdsman, were said to meet just once a year on the 7th day of the 7th month. The Lakota people saw it as the dusty trail left by a giant turtle crawling across the heavens. What all these myths share is the instinct to name what couldn't yet be understood, to turn the unknown into something familiar, almost intimate. Fast forward to the early 20th century, when astronomers finally unraveled the Milky Way's true identity. That soft glow isn't a river or spilled milk. It's the collective light of hundreds of billions of stars, so densely packed in the plane of our spiral galaxy that their combined radiance blurs into a luminous fog. From our vantage point inside this cosmic pinwheel, we're like ants on a record player, seeing the groove of stars edge on rather than face on. But here's what the myths couldn't have guessed. The Milky Way is just one of an estimated 2 trillion galaxies in the observable universe, each with its own epic story. Compare our galaxy to its neighbors and the scale becomes humbling. The Andromeda Galaxy, our closest spiral neighbor, outshines the Milky Way with nearly twice as many stars. The tiny Large Magellanic Cloud, visible from the southern hemisphere, is a chaotic dwarf galaxy being slowly torn apart by our gravitational pull. And then there's Messier 87, a monstrous elliptical galaxy 55 million light-years away, home to a supermassive black hole whose shadow was captured in humanity's first ever black hole image. Modern telescopes have peeled back the Milky Way's layers like an interstellar onion. Infrared imaging reveals stars hidden behind clouds of cosmic dust. Radio telescopes map the delicate filaments of hydrogen gas weaving through its arms, and the Gaia mission has plotted the positions and motions of over 1 billion stars, creating a 3D map so precise it shows our galaxy isn't the perfect spiral we once imagined. It's warped, twisted by past collisions with smaller galaxies, still vibrating like a struck gong. Yet for all our scientific progress, the Milky Way hasn't lost its mythic power. It remains a bridge between the ancient and the cutting edge, a reminder that every culture's stories were their first astronomy textbooks. The next time you stand under that shimmering band of light, remember, you're not just looking at stars, you're witnessing the legacy of human wonder, stretching from campfire tales to space telescopes, all written in the language of the cosmos. It seems like common sense when summer scorches the land, surely Earth must be snuggled closest to the sun, soaking up those extra rays. But here's the cosmic curveball. Our planet is actually farthest from the sun during the northern hemisphere's summer months. This counterintuitive truth hinges on a celestial quirk that reshapes how we think about seasons. Earth's axial tilt, not its distance from the sun, dictates whether we're sweating in tank tops or shivering in snow boots. Consider this: every January, Earth reaches perihelion, its closest approach to the sun, at around 91 million miles away. Yet it's the dead of winter for half the globe. 6 months later, we hit aphelion, our farthest distance, 94 million miles, right when barbecue season kicks into high gear. The difference between these 2 points is about 3%, hardly enough to account for the dramatic swing between heat waves and blizzards. The real orchestrator of seasons is Earth's 23.5-degree tilt, a stubborn lean inherited from a cataclysmic collision billions of years ago. As our planet orbits, this tilt angles one hemisphere persistently toward the sun for months at a time, bathing it in longer, more direct daylight while leaving the other half in chilly twilight. So why does this myth endure? Blame the illusion of proximity. Ancient skywatchers from Egypt to China logically assumed more sun equaled more heat, weaving myths of fiery gods drawing nearer to Earth. Even today, textbooks often oversimplify the relationship between distance and temperature, leaving room for confusion. But the real kicker: seasons are flipped in the southern hemisphere. Australia's Christmas barbecues happen at perihelion, proving distance plays second fiddle to tilt. The persistence of this misconception reveals something profound about human intuition. We trust our immediate senses. The sun feels closer when it's blistering hot over invisible astronomical mechanics. Yet the truth is written in the ice cores of Antarctica and the cherry blossoms of Japan, cyclical patterns orchestrated not by our planet's path, but by its elegant, unwavering tilt. Next time you complain about the summer heat, remember, you're basking in sunlight that's traveled 3 million miles farther than the winter rays, all because a knock from space left Earth forever leaning into the cosmic wind. The full moon has long been blamed for madness, mayhem, and midnight transformations. Think werewolves howling at the sky or emergency rooms overflowing with lunatics. Even the word itself, lunatic, comes from the Latin luna, meaning moon. Police officers swap stories about busier shifts during full moons, nurses brace for chaotic nights, and folklore warns of cursed transformations. But when scientists actually crunch the numbers, a startling pattern emerges. There's zero reliable evidence linking lunar phases to human behavior. So why does this myth cling so stubbornly to our collective imagination? Dozens of studies have tried and failed to find a connection between the moon and spikes in crime, hospital admissions, or mental health crises. One massive analysis published in Current Psychiatry Reports examined over 100 studies on lunar effects and found no statistically significant trends. Emergency rooms don't see more patients during full moons. Crime rates don't mysteriously surge. Even sleep studies, which once suggested people slept worse under a full moon, couldn't replicate their findings under controlled conditions. The moon's gravitational pull, while strong enough to move oceans, is far too weak to disrupt the delicate chemistry of the human brain. To put it in perspective, the tug you feel from a mosquito landing on your arm is stronger than the moon's pull on your body. Yet the myth persists, fueled by confirmation bias and centuries of storytelling. Full moons are brighter, casting an eerie glow that might make people more active or more noticeable. If a strange crime happens on a well-lit night, it's easier to blame the moon than sheer randomness. Literature amplified the idea, from Shakespeare's Othello warning, "It is the very era of the moon," to Gothic tales of werewolves and madness. Even today, pop culture reinforces the trope with horror movies timing supernatural events to lunar cycles. The moon became a scapegoat for chaos, a way to explain the unexplainable in an era before psychology or neuroscience. But here's the twist: the moon does influence life on Earth, just not in the way myths suggest. Coral reefs synchronize their spawning to lunar phases. Nocturnal animals adjust their hunting patterns to moonlight. Even some plants, like the ephedra shrub, alter their reproductive cycles with the moon's rhythm. These real effects highlight how ancient cultures might have observed genuine lunar connections in nature, then extrapolated them wildly to human behavior. The next time someone claims the full moon made them act out, remember, the real magic isn't in the moon's power over us, but in our timeless urge to weave the cosmos into the story of being human. That magical twinkle in a star's eye isn't a sign of its size or personality. It's actually Earth's atmosphere playing tricks on us. When starlight streaks through 95 miles of shifting air layers, it bends, scatters, and wobbles like a dime at the bottom of a swimming pool. The more turbulent the atmosphere, the more dramatic the dance, which is why stars low on the horizon, like Sirius on a winter's night, put on such a frantic light show. Their rays slice diagonally through thicker, choppier air compared to stars overhead, amplifying the shimmer. This atmospheric interference, called scintillation, has fooled sky watchers for millennia. Ancient astronomers assumed twinkling stars were physically flickering, perhaps celestial lanterns sputtering in the cosmic wind. Even Galileo's early telescopes couldn't resolve the mystery since they magnified the blurring effect. But modern science reveals the truth. Stars themselves burn steadily. Their light only appears to waver because pockets of warm and cool air act like invisible lenses, constantly refracting the light in random directions. It's the same reason distant city lights seem to dance on hot summer nights. Sirius, the brightest star in our sky, becomes a twinkling superstar precisely because of its brilliance. Its intense light amplifies the atmospheric distortion, sometimes flashing vivid reds and blues as different wavelengths bend at slightly different angles, a phenomenon called chromatic aberration. Near the horizon, Sirius can look like a disco ball caught in a windstorm, while high overhead it stabilizes to a calmer glow. Planets, by contrast, barely twinkle at all. Their apparent size, tiny disks rather than pinpricks of light, averages out the distortions, making them shine with steady confidence. Next time you gaze up, try this experiment. Hold your hand at arm's length and compare stars near the horizon to those directly above. You'll witness atmospheric turbulence in action, a reminder that even the clearest night sky is a living, rippling lens. Those twinkles aren't flaws, they're Earth's signature written across the cosmos. Space isn't silent, it's an orchestra waiting to be heard. The old myth that the universe is a soundless vacuum crumbles when you listen to NASA's eerie sonifications, where black holes hum like bass notes and galaxies sing in radio waves. The catch, sound as we know it, vibrations traveling through air, can't exist in the near-empty void between stars, but that doesn't mean the cosmos is mute. It just speaks in frequencies we've had to learn to translate. Take the Perseus galaxy cluster 250 million light-years away. In 2003, astronomers detected pressure waves rippling through its superheated gas, a cosmic B-flat 57 octaves below Middle C, far too deep for human ears. NASA Chandra X-ray Observatory captured these waves, and scientists scaled them up by quadrillions of times, giving us the haunting sound of a black hole's roar. It's not music in the traditional sense, but it's proof that even the darkest corners of space pulse with rhythm. Then there's the Milky Way's own supermassive black hole, Sagittarius A. In 2022, researchers turned its X-ray flares into a crackling, otherworldly soundtrack like interstellar static overlaid with deep, resonant tones. These sonifications aren't just artistic whimsy, they're tools. By converting light and particle data into sound, astronomers can detect patterns invisible to telescopes. A distant exoplanet's magnetic field might whistle when graphed as audio, or a collapsing star's gamma rays chime at frequencies that reveal its structure. The universe's soundtrack hides in unexpected places. Saturn's rings emit radio waves that, when processed, resemble rainfall on a tin roof. Jupiter's magnetosphere crackles like a campfire, its charged particles dancing to the planet's magnetic tune. Even the Big Bang left an echo, the cosmic microwave background, which, if compressed into a single note, would resonate as a deep drone nearly 40 octaves below what humans can perceive. Why does this myth of silence endure? Because we're prisoners of our biology. Our ears evolved for Earth's thick atmosphere, not the sparse plasma of space. But with technology as our translator, we're finally hearing what ancient stargazers could only imagine. A cosmos alive with vibration, where black holes don't just devour, they sing. Look up at the night sky, and you'll probably describe the stars as tiny white specks like diamond dust scattered on black velvet. But that's just an illusion created by our eyes struggling to process faint light. The truth, stars blaze in a rainbow of colors, each hue a fiery clue to their temperature, age, and fate. Take Orion, the hunter, striding across the winter sky. His shoulder, the red supergiant Betelgeuse, glows like a dying ember at 3,200 degrees Fahrenheit, while his foot, the blue supergiant Rigel, burns nearly twice as hot, a searing 12,000 degrees. These aren't just pretty differences, they're cosmic name tags, telling us which stars are newborns and which are on the brink of collapse. Why don't we see these colors at a glance? Our night vision relies on rod cells, which are terrible at detecting color in low light. But point even a basic telescope at the stars and the palette emerges. Red stars like Betelgeuse are the coolest, though cool is relative, they're still scorching by earthly standards. They've exhausted most of their hydrogen fuel, puffing up like bloated balloons as they near death. Yellow stars like our Sun are middle-aged and stable, while blue stars like Rigel are the cosmic teenagers, massive, hot, and destined to burn out fast in spectacular supernovas. The science behind these colors is surprisingly hands-on. Think of a blacksmith heating metal. First it glows dull red, then yellow, and finally white hot. Stars operate on the same principle, with their color dictated by surface temperature. Wien's law, a cornerstone of astrophysics, mathematically links a star's peak wavelength to its heat. Blue stars emit most of their light at shorter, hotter wavelengths, while red stars radiate at longer, cooler ones. For a real-time demo, glance at Sirius, the brightest star in our sky. Through binoculars, it shimmers with a steely blue tint, a dead giveaway of its frenzied nuclear reactions. Contrast that with Antares, the heart of Scorpius, which pulses like a rusty stoplight, its red hue betraying its status as an aging supergiant. Even our own Sun, which seems white at noon, reveals its yellowish nature at sunrise and sunset when its light filters through Earth's atmosphere. These colors aren't just aesthetics, they're survival guides for astronomers. By analyzing a star's hue, scientists can estimate its size, lifespan, and chemical makeup. Red giants often harbor carbon and oxygen in their atmospheres, elements forged in their cores, while blue stars are laced with helium, a byproduct of their breakneck fusion. The next time you stargaze, try squinting just enough to let the colors emerge. That faint twinkle isn't just a point of light, it's a beacon broadcasting its life story across the void. Open your horoscope app or flip through a newspaper's astrology column, and you'll find the same 12 zodiac signs that have defined star-powered personalities for centuries. But here's the celestial secret your astrologer won't tell you. There's a 13th constellation elbowing its way into the zodiac's exclusive club, Ophiuchus, the serpent bearer. This sprawling group of stars straddles the ecliptic, the sun's apparent path across the sky, just like its more famous neighbors. Yet somehow it got kicked out of the astrological lineup over 2,000 years ago. The reason? Blame ancient politics, not astronomy. The Babylonians, master skywatchers who carved the zodiac into 12 equal slices around 500 BC, faced a practical problem. Their calendar needed 12 months to sync with lunar cycles, so they shoehorned the sky into 12 tidy signs, ignoring Ophiuchus despite its obvious presence. This mathematical convenience stuck, passed down through Greek and Roman traditions until it became gospel. But the cosmos doesn't care about human bookkeeping. Thanks to Earth's wobbly axis, a phenomenon called precession, the Sun now spends more time in front of Ophiuchus, 18 days, than it does in Scorpio, just 7. That means if you were born between November 29th and December 17th, modern astronomy would technically label you an Ophiuchus, not a Sagittarius. So why hasn't astrology updated its charts? Tradition trumps truth in the zodiac's case. Introducing a 13th sign would upend the entire system. Your Scorpio friend might suddenly be a Libra, or your Taurus partner an Aries. The backlash would make Y2K look tame. NASA even jokingly pointed out Ophiuchus's exclusion in a 2016 blog post, causing panic among astrology enthusiasts who mistook a light-hearted astronomy lesson for an official cosmic reshuffling. But here's where it gets ironic. Ancient astrologers might have actually respected Ophiuchus. Linked to the Greek god Asclepius, the constellation symbolizes healing and wisdom, traits that align neatly with astrology's focus on destiny and growth. Some modern astrologers quietly acknowledge it as a hidden sign, attributing traits like intuition and transformation to those born under its stars. Meanwhile, astronomers shrug to them. The zodiac is just a convenient fiction, a human-made grid overlaid on a dynamic, ever-shifting sky. The next time someone asks your sign, consider this: the stars overhead today aren't where they were when your horoscope was written. Whether you cling to the classic 12 or embrace the forgotten 13th, the real lesson isn't about signs, it's about how we've always bent the universe to fit our stories, not the other way around. Venus might be called Earth's twin, but if it is, it's the evil one from a twisted mirror universe. At first glance, the similarities seem convincing. Both planets are roughly the same size, made of similar rocky material, and orbit relatively close to each other in the Sun's habitable zone. But that's where the resemblance ends. While Earth became a lush oasis, Venus transformed into a crushing, scorching hellscape with an atmosphere so thick it could flatten a submarine. The Soviet Union's Venera probes gave us our first harrowing glimpse of this alien world. In 1975, Venera 9 landed on Venus and survived just 53 minutes before succumbing to surface temperatures nearing 900 degrees Fahrenheit, hot enough to melt lead. Its cameras captured eerie, distorted images of sharp volcanic rocks bathed in an orange haze, the only photographs ever taken from Venus's surface. The atmosphere, 96% carbon dioxide, presses down with 92 times the force of Earth's air, equivalent to being 3,000 feet underwater. Sulfuric acid clouds race around the planet at hurricane speeds, completing a full rotation every 4 Earth days, while the surface below takes 243 days to drag through a single-day night cycle. Why did Venus go so wrong? Blame a runaway greenhouse effect. Billions of years ago, it might have had oceans like Earth's, but as the sun grew hotter, Venus's water vapor evaporated, trapping heat that baked carbonates out of the rocks. This released even more CO2, creating a vicious cycle that never stopped. Today, its atmosphere traps so much heat that even the night side never cools down. Earth narrowly avoided this fate. Our carbon got locked away in limestone, oceans, and life, while Venus became a cautionary tale of climate change gone apocalyptic. Yet Venus still holds clues to our own planet's future. Studying its atmosphere helps scientists model extreme warming scenarios, revealing how delicate Earth's balance really is. The next time someone calls Venus Earth's twin, remember, siblings can grow up in the same house and still turn out nothing alike. The idea of a sinister, dark side lurking on the moon is pure fiction, but it's fiction with a surprisingly long shadow. This myth didn't start with Pink Floyd's legendary album, though they certainly cemented it in pop culture. The roots go back to 19th century Gothic literature, where writers like Edgar Allan Poe and H.G. Wells spun tales of lunar malevolence. In Wells's The First Men in the Moon, published in 1901, the moon's far side is home to a hive of aggressive insectoid creatures, while Poe's The Unparalleled Adventure of One Hans Fall describes it as a place of grotesque landscapes and lurking danger. These stories tapped into a primal fear, what hides in the places we can't see. Science, of course, tells a far less dramatic story. The moon's far side isn't evil, it's just unexplored. Until the Soviet Union's Luna 3 probe snapped the first grainy photos in 1959, humanity had never laid eyes on it. What we found wasn't a nightmare realm, but a landscape pockmarked with even more craters than the familiar near side, thanks to eons of unprotected bombardment from space. The lack of large, smooth seas of hardened lava common on the Earth-facing side gives it a more rugged, alien appearance, but there's nothing inherently ominous about it. Pink Floyd's The Dark Side of the Moon, released in 1973, wrapped this mystery in psychedelic soundscapes, turning the phrase into shorthand for hidden madness and existential dread. Yet even the album's iconic prism cover reflects light, not darkness, a nod to the scientific truth that both sides of the moon bask in sunlight equally. The real dark side is just a trick of perspective, a place forever turned away from Earth's prying eyes, not from the sun's life-giving rays. Modern lunar missions have demystified the far side further. China's Chang'e 4 lander, which touched down in 2019, revealed a desolate but scientifically fascinating terrain, rich with clues about the moon's violent formation. Radio astronomers even dream of placing telescopes there, shielded from Earth's constant radio chatter. The far side isn't evil, it's a silent witness to cosmic history waiting to share its secrets. So why does the myth endure? Because darkness in stories is never just about light. It's about the unknown, and nothing fuels imagination like a blank space on the map, even when that map hangs in the sky. When Halley's Comet streaked across the sky in 1910, newspapers screamed that its tail would poison the planet with cyanogen gas, sparking a wave of panic that had people sealing windows, buying comet pills, and even fleeing to churches to pray for salvation. This wasn't just tabloid hysteria, it was the latest chapter in a millennia-old fear that comets were harbingers of doom. Ancient Chinese astronomers called them broom stars, sweeping disaster into the world. Julius Caesar's assassination was said to be foretold by a comet's glow, and William the Conqueror interpreted Halley's appearance in 1066 as a divine endorsement for invading England. For centuries, these icy wanderers were seen as celestial curses, their sudden appearances blamed for plagues, wars, and the fall of empires. The 1910 frenzy reached absurd heights thanks to a perfect storm of bad science and sensationalism. Astronomers had recently discovered cyanogen in comet tails, and though the gas would be hopelessly diluted by the time it reached Earth, newspapers ran headlines like "Comet poison to kill all life." Entrepreneurs sold gas masks and anti-comet umbrellas, while con artists hawked sugar pills as cosmic antidotes. In Oklahoma, a group even tried to sacrifice a virgin to appease the heavens until police intervened. The comet passed without incident, but the fear lingered, proving how easily ancient superstitions could hijack modern minds. Then came Rosetta, the European Space Agency's mission that changed everything. In 2014, after a decade-long journey, Rosetta's lander, Philae, touched down on Comet 67P, a craggy, duck-shaped relic from the solar system's birth. What it found wasn't a bringer of doom, but a time capsule. The comet's water had a different isotopic signature than Earth's, challenging the idea that comets delivered our oceans. Its surface was porous, covered in organic molecules like amino acids, building blocks of life that might have seeded our planet. Instead of death, comets could have been cosmic gardeners, sprinkling the ingredients for biology across the young Earth. The Rosetta mission didn't just demystify comets, it rewrote their role in our story. Those icy visitors aren't omens, they're archivists carrying clues about how planets form and how life might have begun. The next time Halley's Comet returns in 2061, we won't be boarding up our windows. We'll be cheering, knowing it's not a portent of disaster, but a messenger from the dawn of the solar system, one that's still teaching us how we got here. Space might conjure images of endless, icy darkness, a frozen void where temperatures plummet to hundreds of degrees below zero. But the truth is far more extreme. Space isn't just cold. It's a place of wild, violent temperature swings where an object can bake in scorching heat on one side while the other side freezes solid. Take Mercury, the solar system's smallest planet. During the day, its surface roasts at 800 degrees Fahrenheit, hot enough to melt lead, while at night it plummets to -290 degrees, a 1,000-degree roller coaster caused by its whisper-thin atmosphere which can't hold or distribute heat. This isn't just a planetary quirk. Spacecraft face the same brutal dance between fire and ice. Without an atmosphere to moderate temperatures, materials exposed to direct sunlight can reach 250 degrees, while shaded sections drop to -250 in the same moment. Engineers call this thermal shock, and it's one of the biggest challenges in spacecraft design. Imagine a satellite with solar panels blazing in sunlight while its instruments hide in shadow. Left unchecked, the metal would warp, electronics would fail, and seals would crack. The Hubble Space Telescope, for example, orbits Earth every 90 minutes, cycling between blistering sunlight and deep cold 16 times a day. To survive, it's wrapped in reflective insulation like a high-tech thermos, while heaters and radiators work overtime to balance the extremes. The root of this chaos lies in space's emptiness. On Earth, heat transfers through air or water, smoothing out temperature differences. But in the vacuum of space, the only way heat moves is through radiation. Slow, inefficient infrared waves that can't keep up with the rapid swings. That's why spacesuits are layered with aluminized fabric to reflect solar radiation while trapping body heat. Even the Apollo missions faced thermal nightmares. The lunar module had to withstand 300-degree shifts between moon, day, and night, while astronauts' footprints in the dust became permanent records, unaffected by wind or weather that might erase them. But here's the twist: some of the coldest places in the universe exist alongside these infernos. Shadowed craters at the moon's poles dip to -400 degrees, trapping water ice for billions of years. Meanwhile, the Boomerang Nebula, a cloud of gas 5,000 light-years away, holds the record for coldest natural place ever measured. -458 degrees, just 1 degree above absolute zero. Space doesn't pick a side in the battle between hot and cold. It's both at once, a realm where temperature isn't a single number but a dizzying spectrum of extremes. So why does the always cold myth persist? Because we're creatures of Earth, conditioned to think of shade as cool and space as the ultimate shade. But reality is stranger. Space doesn't have a temperature at all, it's what's in it that burns or freezes. Whether it's a spacecraft dodging solar flares or a comet's tail glowing in the void, the cosmos refuses to be boxed into our simple assumptions. Next time you shiver at the thought of space's cold, remember, it's not the cold that'll kill you. It's the part where you boil alive in sunlight just inches from your frozen shadow. It's one of the most persistent conspiracy theories of all time. The claim that NASA faked the moon landings, filming them in a desert studio to win the Cold War space race. Skeptics point to the American flag appearing to wave in a vacuum, strange shadows crisscrossing the lunar surface, and the absence of stars in Apollo photos as proof of a hoax. But let's set the record straight. Every single one of these so-called clues crumbles under the weight of basic physics and overwhelming evidence. Take that infamous flag. Footage shows it moving as astronauts plant it, which conspiracy theorists say couldn't happen without air. But here's what they miss: the flag wasn't waving, it was vibrating. The astronauts twisted the pole to drive it into the tough lunar soil, causing the fabric to ripple momentarily like a spring. With no air resistance to dampen the motion, those ripples lasted longer than they would on Earth. The flag's wrinkle-resistant design, complete with a horizontal rod to keep it extended, only added to the illusion of movement. Then there are the shadows. Critics argue that multiple light sources must have been used because some shadows don't run parallel, but the moon's uneven terrain explains this perfectly. When sunlight hits slopes, craters, and hills, it creates angled shadows just like a flashlight would on a rocky path. The Apollo photos even show debris kicked up by the lunar module scattering light in all directions, something no Hollywood set could replicate in the 1960s. But the most irrefutable proof isn't in photos, it's literally on the moon's surface. During Apollo 11, 14, and 15, astronauts left behind laser reflectors, arrays of tiny mirrors that scientists still use today. By firing lasers at them from Earth and measuring the light's return time, we've calculated the moon's distance down to the millimeter. These reflectors only work if placed by hand. No robotic mission could have positioned them with such precision. Even China's Chang missions have relied on them for navigation. Then there are the moon rocks, 382 kilograms of them. each chemically distinct from Earth minerals and bearing marks of prolonged exposure to solar wind and micrometeorite impacts. Labs worldwide have studied these samples, confirming their extraterrestrial origin. No secret film set could have forged something that spent billions of years bombarded by cosmic rays. Perhaps the most compelling evidence, though, comes from the astronauts themselves. 12 men walked on the moon, and not one, despite divorces, financial struggles, or even public scrutiny, ever cracked under pressure to confess. Buzz Aldrin famously punched a conspiracy theorist who accused him of lying. Meanwhile, the Soviet Union, America's fiercest rival, never disputed the landings. Their tracking stations monitored the missions in real time, and their own lunar probes later photographed Apollo landing sites. The moon landing hoax myth endures not because of evidence, but because it taps into a deeper human instinct to distrust authority and romanticize secrecy. But science doesn't care about our skepticism. The reflectors keep bouncing light, the rocks keep revealing cosmic secrets, and the boot prints left in 1969 remain untouched, frozen in time on an airless world where no wind will ever blow them away. Saturn may wear the solar system's most dazzling crown, but it's far from the only planet with rings. Jupiter, Uranus, and Neptune all sport their own ethereal halos, some so faint they weren't discovered until spacecraft flew close enough to spot them. When Voyager 1 glided past Jupiter in 1979, its cameras revealed a gossamer-thin ring system, barely visible from Earth, made of dust kicked up by meteorite impacts on the planet's inner moon. These rings lack Saturn's icy brilliance, shimmering instead like a ghostly cobweb stretched across the void. Then there's Uranus, tipped sideways like a knocked-over bowling ball, with rings to match its oddball orientation. Discovered in 1977 when astronomers watched the planet pass in front of a star, its rings momentarily dimmed the starlight like a celestial eyelid blinking. Unlike Saturn's icy chunks, Uranus's rings are cold dark, likely packed with organic compounds altered by radiation. Neptune's arcs, spotted by Voyager 2 in 1989, are even stranger, clumpy, uneven segments named after mathematicians like Adams and Leverrier, as if the planet couldn't decide between a full ring or none at all. But Saturn's rings remain the undisputed masterpiece. The Cassini mission, which orbited Saturn from 2004 to 2017, revealed them in jaw-dropping detail. Towering ice cliffs taller than the Rocky Mountains, propeller-shaped moonlets carving gaps like cosmic lawnmowers, and even oxygen molecules embedded in the ice, hinting at complex chemistry. Scientists now think these rings might be younger than some dinosaurs, perhaps only 100 million years old, a fleeting decoration in cosmic time. So why does Saturn get all the glory, blame sheer spectacle? While other planets whisper their rings, Saturn shouts. From Earth, even a modest telescope reveals its iconic loops, a celestial bullseye that's inspired everything from Galileo's sketches to sci-fi skyscapes. But the real lesson here is how much we still have to learn. Jupiter's rings might hold clues about its violent meteorite history. Neptune's arcs could be collapsing into moons right now. And Saturn, its rings are a temporary wonder, destined to either spiral into the planet or scatter into space, a reminder that even the grandest cosmic features are just passing shows in an ever-changing universe. When you look up at the night sky, you're staring into a cosmic time machine. Those twinkling stars overhead aren't necessarily still there. They could already be gone, their light just now reaching us across unimaginable distances. This eerie fact comes down to the nature of light itself, which takes time to travel through space. Even at its blistering speed of 671 million miles per hour, light from distant stars can take centuries or millennia to cross the void to Earth. Take Betelgeuse, that fiery red giant in Orion's shoulder. Located about 650 light-years away, the light we see tonight left the star around the time the Black Death was ravaging Europe. Given its volatile nature, It's a ticking supernova. Astronomers speculate Betelgeuse may have already exploded without us knowing. We'd continue seeing its steady glow for centuries until the light from its death finally reaches us in a spectacular celestial fireworks display. The delay makes stargazing an act of archaeology, where we're always seeing stars as they were, not as they are. Now consider Proxima Centauri, our nearest stellar neighbor at just 4.2 light-years away. Its light takes a mere 4 years and change to reach us, meaning we see it as it looked when the last Olympics were held. While that might seem like a minor delay compared to Betelgeuse, it still means we're always slightly out of sync with even our closest cosmic companions. If Proxima Centauri suddenly vanished today, we wouldn't know until 2028. This time lag plays tricks with perspective. The famous Pleiades star cluster appears as a tight grouping of young blue stars, but in reality, some members are dozens of light-years closer than others. We just see them projected together like a cosmic illusion. Even our own sun's light takes 8 minutes to reach Earth, so if it blinked out unexpectedly, we'd enjoy 8 more minutes of ignorant bliss before darkness fell. The most mind-bending implication: some stars we see tonight might not just be dead, they could be completely gone, their matter recycled into new stars and planets. When you trace the light from distant galaxies billions of light-years away, you're seeing baby pictures of the universe itself, snapshots from when galaxies were first forming. Every glance upward is a journey through time where the present is always just out of reach, and the stars whisper stories from the past. The shimmering curtains of the aurora borealis have long been painted as the gods' handiwork. Viking legends spoke of the armored Valkyries riding across the night sky, their polished shields reflecting celestial fire. Even today, standing beneath those undulating green and purple ribbons, it's easy to believe in magic, but the truth is far more electrifying. This spectacle is the fallout of a violent cosmic storm, where rivers of charged particles from the sun smash into Earth's invisible magnetic shield at 1,000,000 miles per hour. Picture the sun not as a tranquil orb, but as a churning cauldron of plasma, constantly hurling protons and electrons into space. This solar wind, a supersonic stream of charged particles, races toward Earth like an interstellar tsunami. When it hits our magnetosphere, the planet's protective magnetic bubble, most gets deflected harmlessly into space. But some particles slip through near the poles, where magnetic field lines funnel them downward like water spiraling down a drain. As these invaders collide with oxygen and nitrogen in our upper atmosphere, they dump their stolen energy, sparking a luminous frenzy. Oxygen glows green or red, depending on altitude, while nitrogen burns blue or purple, painting the sky with otherworldly hues. The ancients weren't entirely wrong to see divinity here. In Norse mythology, the aurora was Bifrost, the flaming bridge linking Asgard to Midgard. Finnish folklore claimed it was the Arctic fox dashing across snowfields, kicking up sparks. But modern science reveals something just as awe-inspiring. We're witnessing Earth's magnetic field flexing under solar assault, a force field so vast it stretches halfway to the moon on the sunward side and tapers into a 1,000,000-mile tail on the night side. Without it, those same particles would strip away our atmosphere, leaving us as barren as Mars. Satellites like NASA's Artemis mission have captured this battle in real time. Gigantic magnetic ropes, called flux transfer events, form when solar wind tears open temporary rips in our defenses, flooding the upper atmosphere with energy. The resulting light show follows patterns invisible to the naked eye: swirling vortices near dawn, pulsating patches at midnight, each a clue to the magnetosphere's ever-shifting shape. Even the sound of the aurora, long dismissed as imagination, has been recorded. Eerie crackles and pops caused by electrical discharges 60 miles up. Next time you stand beneath the northern lights, remember, you're not just seeing pretty colors, you're witnessing a near miss from a solar storm that could, in a stronger strike, fry satellites and knock out power grids. The same forces that inspired myths now keep our technology and our civilization from short-circuiting. The gods might be gone, but their bridge still burns, a reminder that beauty and danger often dance hand in hand at the edge of space. For decades, whispers of a mysterious Planet X lurking at the solar system's edge have ignited conspiracy theories and fueled doomsday prophecies. The most infamous is Nibiru, a supposed rogue planet said to be hurtling toward Earth to unleash apocalypse, a claim that's been recycled endlessly since the 1970s despite having zero scientific basis. But here's where the story twists. While Nibiru is pure fiction, astronomers are hunting a real, hypothetical world nicknamed Planet 9, a search that's turned fringe fantasy into legitimate astronomy. The Nibiru myth began with writer Zecharia Sitchin's controversial translations of ancient Sumerian texts, which he claimed described a 12th planet with a bizarre, elongated orbit. Conspiracy theorists latched onto this idea, blending it with bogus NASA leaks and misinterpreted Mayan calendar predictions to proclaim Nibiru would collide with Earth in 2012. When that date passed uneventfully, the deadline conveniently shifted to 2017, then 2020, and so on. Telescopes have scanned the skies for decades, including infrared surveys that would have spotted a massive planet moving toward us, but Nibiru remains as elusive as Atlantis. Meanwhile, something far more interesting was unfolding in real astronomy. In 2016, Caltech researchers Konstantin Batygin and Mike Brown noticed peculiar clustering in the orbits of distant icy objects beyond Neptune. These Kuiper belt bodies all angled toward the same patch of sky, as if tugged by something massive. The math suggested a potential culprit, a hidden planet 5 to 10 times Earth's mass, orbiting roughly 20 times farther than Neptune. Unlike Nibiru's doomsday trajectory, Planet 9, if it exists, would follow a stable, elliptical path, taking up to 20,000 years to complete one lap around the Sun. The key difference here is evidence. Nibiru believers rely on cherry-picked ancient texts and viral hoaxes, while Planet 9 proponents point to gravitational anomalies and painstaking orbital calculations. Occam's razor, the principle that the simplest explanation is often correct, cuts through the noise. Kuiper belt oddities could stem from random chance or observational bias, but a hidden planet fits the data neatly without invoking cosmic prophecies. Searchers for Planet 9 have turned up fascinating celestial oddballs like the distant object Sedna, which orbits entirely beyond the Kuiper belt, or the highly tilted Goblin, whose path also hints at unseen forces. But so far, no definitive Planet 9. The Vera C. Rubin Observatory, set to begin scanning the skies in 2025, might finally settle the debate with its unprecedented telescopic power. Whether Planet 9 is found or not, its hunt exemplifies science at its best, following clues, testing hypotheses, and remaining open to revision. Nibiru, on the other hand, is a cautionary tale of how easily myth can masquerade as fact when we ignore the rigor of evidence. The cosmos is strange enough without inventing threats. Sometimes the truth hiding in the shadows is far more thrilling than fiction. Flip the script on everything you've heard about why the sky is blue, because it's not reflecting the ocean's color at all. In fact, the ocean appears blue for the exact opposite reason. It's borrowing its hue from the sky above. This cosmic color swap all comes down to a phenomenon called Rayleigh scattering, where sunlight gets bounced around like a pinball in Earth's atmosphere before reaching our eyes. Picture sunlight as a mixed bag of colored light: red, orange, yellow, green, blue, indigo, and violet, all traveling together. When these rays hit Earth's atmosphere, they collide with nitrogen and oxygen molecules. But here's the catch: shorter wavelengths, the blues and violets, get scattered much more dramatically than the longer reds and yellows. It's like tossing a handful of pebbles into a pond. The smaller ripples go everywhere while the big waves push straight through. That scattered blue light ends up painting the entire sky dome, while the other colors mostly barrel straight down to the ground. Now, why doesn't the sky look violet, since violet light scatters even more than blue? That's where human biology comes in. Our eyes are far more sensitive to blue than violet, and sunlight contains less violet to begin with. So evolution tilted the scales, making us perceive the sky as a brilliant azure rather than a lavender wash. Sunset cranks this phenomenon to extremes. When the sun hangs low, its light must travel through thicker atmosphere, forcing even more blue light to scatter out of view. What remains is the fiery palette of reds, oranges, and pinks, the colors that refuse to be scattered, finally getting their moment to dominate the horizon. For a mind-bending comparison, look to Mars. The red planet's thin, carbon dioxide-rich atmosphere scatters light differently, creating a pinkish sky during the day that shifts to a pale blue at sunset, the exact inverse of Earth's pattern. On Titan, Saturn's largest moon, the nitrogen-heavy atmosphere and organic haze turn the sky a perpetual orange like smog over Los Angeles. These aren't just pretty differences, they're atmospheric fingerprints revealing each world's composition without a single soil sample. So next time someone points to the ocean as the source of the sky's blue, you'll know the truth. That breathtaking canopy above us is really just sunlight playing an ancient game of bumper cars with the air, a reminder that sometimes the simplest natural wonders hide the most dazzling physics. Here's the surprising truth: astronauts floating inside the International Space Station aren't weightless because they've escaped gravity. In fact, Earth's gravity at the ISS's altitude is still about 90% as strong as it is on the ground. So why do they drift like feathers in a breeze? The real answer lies in a concept called microgravity, a delicate dance between falling and missing the ground. Picture this: the ISS isn't just hanging in space, it's plummeting toward Earth at over 17,000 miles per hour. But here's the catch: it's moving sideways so fast that as it falls, the Earth's curvature drops away beneath it at the same rate. This creates a perpetual state of free fall, where the station and everyone inside it are continuously falling together, never actually hitting the surface. It's like a cosmic version of a roller coaster's zero-gravity drop stretched into an endless loop. The astronauts aren't floating away from gravity, they're falling with it, creating the illusion of weightlessness. NASA trains astronauts for this surreal environment using a modified airplane nicknamed the Vomit Comet. This aircraft flies parabolic arcs, sharp climbs followed by free-fall dives, giving passengers about 25 seconds of microgravity at a time. Early trainees learned the hard way why it earned its name. Without gravity to anchor inner ear fluids, spatial disorientation and nausea hit fast. But these flights are crucial for practicing tasks like repairing equipment or maneuvering in bulky suits, all while drifting like human balloons. The physics behind microgravity reveals even stranger quirks. Without constant gravity tugging fluids downward, astronauts' faces puff up as fluids redistribute. Candles burn as tiny blue spheres instead of teardrop flames, and water forms floating globes that can swallow bubbles like alien jellyfish. Even the ISS itself has to account for subtle tidal forces. Earth's gravity is slightly stronger on the station's lower side, creating a tension engineers must factor into its design. Next time you see astronauts flipping effortlessly in zero-G, remember, they're not beyond gravity's reach. They're masterfully riding its edge, a testament to how orbital mechanics turns relentless falling into the closest thing we have to flying. The moon usually takes all the credit for Earth's tides, but the real story is a celestial tug of war happening right over our heads. While the moon's gravity does pull our oceans into those familiar bulges, the sun plays a sneaky, equally critical role, one that's hiding in plain sight twice every month. Think of it like this: the moon is the lead singer of the tidal band, but the sun is the rhythm section, quietly shaping the highs and lows of the ocean's daily concert. Here's how the teamwork unfolds. When the moon and sun align during full and new moons, their gravitational forces combine like synchronized swimmers, creating spring tides. These aren't named for the season, but for the way ocean waters spring higher than usual. High tides climb extra tall, while low tides plunge unusually deep. Picture the Earth sandwiched between these two gravitational giants. The moon's pull yanking the ocean toward it, while the sun's gravity stretches the water from the opposite side. Even though the sun is 27 million times more massive than the moon, it's also 400 times farther away, making its tidal influence about half as strong, just enough to amplify the moon's work without stealing the show. But then there's the sun's second act. During the moon's first and third quarters, when it sits at a right angle to the sun relative to Earth, their forces don't combine, they compete. The sun's gravity now tugs perpendicular to the moon's pull, cancelling out some of its effect. This creates neap tides where the difference between high and low water shrinks dramatically. Coastlines might see just a few feet of tidal swing instead of the dramatic dozen-foot surges of spring tides. Ancient fishermen knew this rhythm intuitively, timing their hauls to these predictable ebbs. The real magic lies in the math. Tidal force depends not just on an object's mass, but on the cube of its distance. That's why the sun, despite its enormity, can't outmuscle the moon's close-range influence. But when their forces align or oppose, the delicate balance shifts visibly. Modern tidal models map this interplay down to the centimeter, accounting for coastal shapes and seafloor topography. Even planets get in on the action. Jupiter's moons Europa and Io experience tidal heating so extreme it melts their interiors, a reminder that gravity's dance isn't just about water. So next time you watch the tide roll in, remember, you're seeing a silent conversation between two stars, one shining bright overhead, the other a distant but insistent whisper, both sculpting the sea's eternal rise and fall. Every few months, headlines scream about an incoming supermoon, a celestial event supposedly so massive it'll trigger chaos, from werewolf outbreaks to catastrophic tides. But strip away the hype and you'll find a far more subtle reality. A supermoon occurs when the full moon coincides with perigee, its closest approach to Earth in its elliptical orbit. At this point, it's about 30,000 miles nearer than at apogee, its farthest point. That might sound like a cosmic close-up, but in practical terms, the difference is barely noticeable unless you're paying close attention. Hold up a dime at arm's length and it'll roughly cover the moon's apparent size in the sky. During a supermoon, that dime might grow to the width of a nickel, a 14% increase in diameter. To the naked eye, it's like comparing a golf ball to a ping-pong ball side by side. Without the reference of its usual size, most people wouldn't spot the difference. Photographers, though, love this subtle boost. It makes the moon appear slightly larger against city skylines or mountain backdrops, but it's no celestial juggernaut. The real mischief begins with the tidal claims. Yes, the moon's gravitational pull strengthens slightly at perigee, but the actual impact is minuscule. A supermoon might add an inch or two to typical high tides, far less than the dramatic surges caused by storms or seasonal winds. Compare that to the myth's portrayal of supermoons as tidal monsters. It's like blaming a candle flame for a forest fire. Even the so-called Proxygean spring tides, the most extreme high tides tied to supermoons, rarely cause more than minor coastal flooding. The moon's phases, new and full, have a far greater tidal influence than its distance. So why does the supermoon myth persist? Blame confirmation bias mixed with a dash of nostalgia. When a supermoon rises, its low position near the horizon creates the famous moon illusion, where it appears unnaturally large due to our brain's trick of comparing it to distant objects like trees or buildings. This psychological quirk, not actual size, fuels the dramatic photos shared online. And let's not forget pop culture's role. Horror movies love linking full moons to madness, while social media algorithms boost eye-catching if exaggerated supermoon posts. The truth is, supermoons are beautiful but benign, a gentle reminder of the moon's rhythmic dance with Earth, not a harbinger of disaster. Next time you see those clickbait warnings, just smile and step outside. That giant moon, it's the same old companion we've had for billions of years, swinging a tiny bit closer for a night, then drifting away again, no werewolves required. We often imagine the universe stretching endlessly in all directions, an infinite expanse where galaxies go on forever. But here's the catch, we don't actually know if the cosmos is infinite. What we can see, the so-called observable universe, is a bubble roughly 93 billion light-years across, containing every star, galaxy, and photon of light that's had time to reach us since the Big Bang. Beyond that, it's like standing on a ship in the ocean. The horizon blocks our view, but that doesn't mean the water stops there. The observable limit isn't about space itself ending, it's about time and the speed of light. Imagine the universe is 14 billion years old because it is. Light from objects farther away than 14 billion light-years hasn't had time to reach us yet, creating a natural boundary. But here's where it gets wild. Cosmic inflation, the theory that the infant universe expanded faster than light itself in the first fraction of a second, suggests space could be much larger than what we see. How much larger? Some calculations hint the entire universe might be at least 10 to the power of 23 times bigger than our observable pocket, a number so vast it dwarfs every grain of sand on Earth. Philosophers and physicists have wrestled with infinity for centuries. Aristotle rejected it outright, insisting nature abhors the infinite. Einstein's equations initially suggested a finite but unbounded universe, like the surface of a balloon expanding in 3 dimensions, where you could travel forever without hitting an edge but never run out of space. Yet modern measurements of cosmic curvature lean toward a flat, potentially infinite universe. The Planck satellite's precision mapping of the cosmic microwave background found no detectable curvature, meaning if the universe does curve back on itself, the bend is too subtle for us to measure, leaving infinity on the table. But infinity isn't just a math problem, it's a mind bender. An infinite universe would mean infinite copies of Earth, infinite versions of you reading this, and even infinite variations where dinosaurs never went extinct. This level 1 multiverse idea stems from simple probability. With infinite space, every possible arrangement of particles must repeat eventually. Critics argue this strays into metaphysics, but supporters counter that it's the logical endpoint of our best cosmological models. Meanwhile, the quantum realm hints at another layer. Some interpretations of quantum mechanics suggest new universes bud off endlessly, creating an infinite multiverse where every quantum possibility plays out. String theory takes it further, proposing a landscape of 10 to the 500 possible universes, each with different physical constants. Whether these count as infinite depends on your definition, but they certainly stretch the imagination. So is the universe infinite? For now, it's the ultimate unanswerable question. Our telescopes can only see so far, our math can only hint at what lies beyond, and our brains evolve to grasp hunting grounds and weather patterns not the true scale of reality. Perhaps infinity isn't something to solve but to marvel at, a cosmic mirror reflecting how much we don't know and how breathtaking the unknown can be. The Great Pyramid of Giza has fueled wild speculation for centuries. How could a civilization without modern technology align a 481-foot stone monument to true north with pinpoint accuracy, all while stacking over 2 million limestone blocks with seams thinner than a credit card? For UFO enthusiasts, the answer is simple. Aliens must have lent a hand, but here's what the chisel marks, payroll records, and archaeological breadcrumbs reveal. The real builders were far more remarkable than any interstellar contractors. Start with the math. The pyramid's near-perfect alignment wasn't achieved with laser pointers from space, but with a simple wooden tool called a merkit, an ancient Egyptian astrolabe that used the stars to track cardinal directions. During the autumnal equinox, when day and night are equal, shadows cast by the merkit could mark true north within a fraction of a degree. As for moving those massive blocks, The discovery of a 4,000-year-old ramp system at Hatnub Quarry shows how workers hauled stones on sledges greased with water, turning friction into a manageable obstacle. Papyrus records from Wadi al-Jarf detail teams of 20 men transporting limestone along the Nile, with shifts organized like a well-oiled machine right down to bonuses paid in bread and beer. Then there are the quarry marks themselves. Hieroglyphs scribbled on foundation stones at Giza read like a prehistoric time card. Vigorous gang, enduring gang, even drunkards of Menkora, proof that real humans, not alien overlords, sweated over every block. Infrared imaging has revealed hidden chambers where laborers likely slept, and the remains of a massive workers' village at Height El Ghurab show bakeries capable of producing thousands of loaves daily. These weren't slaves, as Hollywood often portrays, but skilled tradespeople who took pride in their work. Analysis of their skeletons reveals signs of healed fractures treated with splints, evidence of a society that invested in its workforce. But why does the ancient astronaut myth persist? Partly because scale distorts our perception. The pyramid's sheer size feels impossible until you account for its 20-year construction timeline, a pace of one block placed every 4 minutes during work seasons. Modern experiments like NOVA attempt to build a small pyramid using period techniques, prove it was grueling but feasible. The real marvel isn't how they built it, but why a testament to human ingenuity when driven by collective purpose. Next time someone credits aliens, remind them, the truth doesn't diminish the achievement, it makes it more awe-inspiring. The sun might look like a flaming ball of fire from our safe distance, but calling it a giant fireball is like comparing a nuclear reactor to a campfire. The truth is far more spectacular and far less fiery. Deep in its core, the sun isn't burning fuel the way wood does in a fireplace. Instead, it's a colossal nuclear fusion reactor, smashing atoms together under pressures so extreme they defy earthly physics. Every second, 600 million tons of hydrogen atoms collide with such force that they fuse into helium, converting a tiny fraction of their mass into pure energy, enough to power our entire planet for hundreds of thousands of years. What we see as sunlight isn't the glow of combustion, but the white-hot shimmer of plasma, a fourth state of matter where electrons are ripped from atoms, creating a seething soup of charged particles. This plasma doesn't behave like fire at all. Instead of rising in predictable tendrils, it churns in massive convection currents, with loops and arches sculpted by the sun's own magnetic field. Some of these magnetic loops twist until they snap like overstretched rubber bands, unleashing solar flares with the energy of billions of atomic bombs. The largest flares can erupt with enough force to disrupt satellites, knock out power grids, and even create auroras visible near the equator, all without a single wisp of smoke. Solar storms reveal just how different the sun is from mere fire. In 2012, a massive eruption called the Carrington event missed Earth by just 9 days. Had it hit, modern estimates suggest it could have caused trillions in damage, frying transformers and plunging continents into darkness. Unlike wildfires, which need oxygen to burn, the sun's fury is self-sustaining, fueled by gravity's endless crush and quantum mechanics' strange rules. Even its surface temperature of 10,000 degrees Fahrenheit is misleading. The surrounding corona, a wispy outer atmosphere, inexplicably heats to millions of degrees, a puzzle scientists still struggle to explain. So why does the fireball myth persist? Because our brains are wired to interpret the world through familiar lenses. Flames flicker, the sun flickers. Flames emit light and heat, so does the sun, but the similarities end there. Next time you bask in sunlight, remember, you're not feeling the warmth of a cosmic bonfire. You're being bathed in the glow of a star's nuclear heart, a fusion furnace that's been burning steady for 4.5 billion years and will keep shining long after every earthly fire has turned to ash. We've all seen the headlines, once in a lifetime planetary alignment. accompanied by breathless claims that the cosmos is staging a rare, harmonious event. The truth, planetary alignments are about as rare as a full moon. Take the much-hyped Great Conjunction of Jupiter and Saturn in 2020, when the two gas giants appeared to merge into a single glowing point in the sky. While it was undeniably stunning, this wasn't some celestial anomaly. These giants shake hands roughly every 20 years like cosmic clockwork. The real magic lies not in their rarity, but in the subtle dance of gravity and geometry that makes these meetings possible. The idea of perfect alignment is a trick of perspective. Planets don't actually line up like beads on a string, they just appear to from our vantage point on Earth. Imagine standing in a room with friends scattered at different distances. If everyone steps into the same general sight line from where you're standing, they'll seem to overlap, even though they're still far apart in the room. That's exactly what happens during a conjunction. Jupiter and Saturn, for example, were still 450 million miles apart during their 2020 rendezvous, but because Earth, Jupiter, and Saturn briefly shared a sight line, they looked like celestial neighbors. Historically, these events were seen as omens. The Babylonians recorded conjunctions as divine messages, while medieval astrologers tied them to the rise and fall of kings. Even Kepler famously linked the Star of Bethlehem to a rare triple conjunction of Jupiter and Saturn in 7b. C. But modern astronomy reveals the mundane truth: alignments are inevitable artifacts of orbital mechanics. Jupiter laps Saturn in their race around the Sun every 19.86 Earth years, meaning their conjunctions follow a predictable rhythm. The 2020 event stood out only because it was the closest visible pairing since 1623, a proximity quirk, not a cosmic miracle. For true rarity, look to syzygy, a lineup of 3 or more celestial bodies. A full solar eclipse is a syzygy of the Sun, Moon, and Earth, while a grand planetary alignment like the 6 planets that clustered in 1982 requires even more precise timing. But even these aren't the universe's applause. They're just brief moments when orbits sync up from our earthly viewpoint. The cosmos doesn't care about our calendars. It follows gravity's lead, indifferent to whether we're watching. So why do we keep mythologizing alignments? Because they tap into our love of pattern and meaning. A sky where planets occasionally meet feels more poetic than one where they mindlessly chase ellipses. But the real wonder isn't in their alignment, it's in the clockwork precision that lets us predict them centuries in advance, a testament to how well we've learned to decode the universe's rhythms. Next time you hear about a once-in-a-millennium alignment, smile and nod, then check the math. The stars will keep their dates with or without our fanfare. Space isn't the pristine, empty void we often imagine. It's more like a ghostly ocean teeming with invisible currents. While the vacuum between stars is far emptier than anything we can create on Earth, it's still home to a thin soup of particles known as the interstellar medium. Picture this: every cubic centimeter of so-called empty space contains anywhere from a few atoms to a few thousand, drifting like cosmic dust motes across light years. That might sound negligible until you realize our entire solar system is currently plowing through a cloud of this sparse gas at 45,000 miles per hour, like a ship cutting through phantom waves. The solar wind, a constant stream of charged particles racing outward from the Sun, adds another layer to this tenuous landscape. Near Earth's orbit, this wind averages just 5 particles per cubic centimeter, thinner than the best man-made vacuums. But during solar storms, that number can spike into the hundreds, battering satellites with enough force to degrade electronics over time. Voyager 1, now in interstellar space, still detects these faint ripples, proof that the Sun's influence extends far beyond the planets. In 2012, its instruments picked up plasma wave vibrations, the first direct evidence of interstellar medium particles being pushed around by solar outbursts that occurred years earlier. What's truly surprising is how loud space can be when you listen correctly. Convert those plasma waves into audible sound, and you'll hear eerie whistles and crackles like radio static from the abyss. These aren't sound waves as we know them, they're fluctuations in charged particles, the universe's version of whispering through a cosmic telephone wire. Even Earth's magnetosphere contributes to this hidden symphony, generating ultra-low frequency chorus waves that surround our planet like an invisible force field humming to itself. So why does the perfect vacuum myth persist? Because human experience is grounded in air-filled environments where vacuums mean absolute emptiness. But space operates on different rules, where even nothingness is filled with traces of something, a reminder that nature abhors a true void. The next time you gaze at the stars, remember, you're looking through a transparent ocean, one whose subtle currents have shaped everything from comet tails to the birth of new solar systems. For decades, scientists assumed the moon was a bone-dry wasteland after all. The Apollo missions brought back dusty rocks devoid of even a hint of moisture. But in 2009, NASA L-Cross mission slammed a rocket into a shadowed crater near the lunar South Pole, sending up a plume of debris that contained something revolutionary: water ice. Not just trace amounts, but an estimated 6% water by mass, enough to fill a dozen Olympic swimming pools in that single impact site alone. This discovery shattered centuries of assumptions and opened a new frontier in space exploration, proving that water isn't just an earthly luxury, but a hidden resource waiting in the coldest corners of our cosmic backyard. Where did this lunar water come from? The leading theory points to a bombardment of comets and water-rich asteroids over billions of years. These icy wanderers crashed into the moon, their frozen payloads settling in permanently shadowed craters, deep, sunless pits where temperatures never rise above -250 degrees Celsius. Unlike Earth, where water evaporates or cycles through the atmosphere, lunar water stays trapped in these icy time capsules, undisturbed for eons. Spectroscopy data from later missions like Chandrayaan-1 revealed even more surprises. Molecules of water clinging to sunlit lunar soil, likely formed when solar wind protons reacted with oxygen in the dust. The moon isn't just holding onto ancient ice, it's manufacturing new water right on its surface. The implications for future lunar bases are staggering. Water isn't just for drinking, it's a vital resource that can be split into hydrogen and oxygen for rocket fuel or breathable air. Mining lunar ice could turn the moon into a cosmic gas station, slashing the cost of deep space missions. Imagine a lunar outpost where astronauts harvest their own water instead of hauling it from Earth at $40,000 per gallon. NASA Artemis program is already targeting these polar regions for landing sites, with plans to extract and test ice samples by the end of this decade. Private companies are joining the rush too, designing drills and rovers capable of operating in perpetual darkness. But the real game changer might be what this ice reveals about our solar system's history. Lunar ice isn't just frozen water. It's a chemical record of every comet that ever kissed the moon's surface. By analyzing its isotopes, scientists could trace which cosmic delivery drivers brought water to Earth and the moon, solving the age-old mystery of how our oceans formed. Some theories even suggest the moon's ice might contain organic molecules, the building blocks of life, preserved in deep freeze since the solar system's infancy. So the next time you look up at the moon, remember, its shadows aren't just empty darkness, they're icy vaults holding secrets to our past and the keys to humanity's future among the stars. You might think city lights have erased the stars completely, turning the night sky into a washed-out void, but even in the brightest urban jungles, the cosmos refuses to be fully silenced. While light pollution does drown out fainter stars, a handful of celestial heavyweights still punch through the glow, defying the assumption that urban stargazing is pointless. Take Sirius, the brightest star in our sky, blazing 25 times more luminous than our sun. On a clear night, even from Times Square, its diamond-like gleam cuts through the orange haze if you know where to look. Orion's belt, that iconic trio of stars, often survives the light bath too, forming a faint but recognizable slash above rooftops. The real culprit isn't just the volume of artificial light, it's the kind. Old-fashioned sodium vapor street lamps with their yellow-orange glow are actually gentler on the night sky than modern LED replacements. Those energy-efficient LEDs emit broader spectrums of blue light, which scatter more aggressively in the atmosphere, creating the luminous domes that blot out stars. Cities like Tucson, Arizona, have adopted dark sky-friendly LEDs with warmer color temperatures, proving urban centers don't have to sacrifice visibility for sustainability. For determined city dwellers, tricks exist to reclaim the cosmos. A simple cardboard tube, a light pollution filter you can make at home, can block peripheral glare, funneling your gaze upward. Mobile apps like Night Sky or Sky View use augmented reality to overlay constellations on your screen, acting as cosmic cheat sheets. Even timing matters, venturing out after midnight when some lights dim, or during a blackout, planned or otherwise, reveals stars you'd swear had vanished. But the fight for starlight goes beyond DIY hacks. Dark sky reserves, like Utah's Natural Bridges National Monument or Scotland's Galloway Forest Park, are sanctuaries where artificial light is strictly controlled. These zones aren't just for astronomers' studies. Show excessive nighttime light disrupts ecosystems, from disoriented sea turtles to confused migratory birds. Even human health suffers. Prolonged exposure to bright nights correlates with sleep disorders and mood imbalances. The myth that cities erase the stars speaks to a deeper truth. We've traded constellations for convenience. Yet resilience lingers overhead. Catching Sirius from a fire escape or spotting Orion between skyscrapers becomes an act of rebellion, proof that wonder doesn't require wilderness, just a willingness to look up. From ancient stargazers whispering tales of celestial omens to modern astronomers decoding the physics behind the myths, these stories reveal something profound about humanity. We've always sought to bridge the gap between what we see in the heavens and what we long to understand. The myths we've unraveled aren't just mistakes, they're stepping stones, blending cultural imagination with scientific discovery. Whether it's the misunderstood dark side of the moon or the illusion of planetary alignments, each misconception carries a hidden truth about how we've navigated the cosmos across centuries. What makes these myths endure isn't ignorance, it's the human need to find patterns, meaning, and wonder in the vast unknown. The same impulse that led the Babylonians to chart Venus's movements now drives us to search for exoplanets or probe black holes. The difference today, we have tools to test our stories against reality. Yet even as science corrects the record, the poetry of those old legends lingers. There's magic in knowing that Polaris, the steadfast North Star, guided enslaved people to freedom just as surely as it helps pilots navigate today, or that the same solar storms Vikings once blamed for auroras now threaten our satellites. So where do we go from here? The night sky is still the world's oldest classroom, and every glance upward is a chance to question, explore, and reconnect with that timeless curiosity. Grab a pair of binoculars and trace the real colors of stars in Orion's belt. Download NASA Sky View app to hunt for planets hiding in plain sight. Or simply step outside during the next meteor shower and let yourself marvel, not just at the science, but at the generations before you who saw those same streaks of light and dared to dream up explanations. The cosmos doesn't need myths to be awe-inspiring, but our myths need the cosmos to keep evolving. So keep looking up, keep questioning, and remember, every time you debunk a celestial tall tale, you're participating in humanity's oldest tradition, rewriting the stories we tell about the stars, one discovery at a time.